Okay, well, good morning, everyone. Thanks for joining us for our virtual seminar series. This morning we have Marcus Knudson from Sandia. He'll be talking about ongoing work at the Z Machine at Sandia. And I wanted to point out a couple things. We have the Topical Group's website up. There are links to past and seminars, as well as the recordings from some of those seminars. The videos of those will be available for a few months after the talk. We'd really like to get your feedback on the seminar series, so feel free to email me, or you can post them on the website. You have to be an APS member to post there, I believe. Most of you already saw that the shock compression conference has been postponed, probably until the summer of 22. Stay tuned for more details. And finally, if you have suggestions for future speakers, please send them to me, or today you can type them in the chat if something comes to mind. We'd love to hear them. And now let's go ahead and get started with Marcus's talk. Marcus got his PhD at Washington State and joined Sandia in 1998 and played an integral role in turning the pulse power Z Machine into one of the premier platforms for shock physics research in the world. And without taking up any more time, I'll turn it over to Marcus.
All right, well, thanks, Tracy, for that introduction, and thanks for the opportunity to give this presentation, the seminar. What I thought I'd talk about was the interplay that we have developed over the years in combining the experimental platform at Z with condensed matter theory to really try to understand what we're seeing in these experiments. I'm going to talk quite a bit about hydrogen today, or deuterium. All of this work is done in collaboration with Mike Desjardins, so he's done the theoretical work that I'll be talking about. And also, we've had an ongoing collaboration with the University of Rostock, both in the theoretical side and also, some of the experimental results I'll show are part of the fundamental science program at Z, which the University of Rostock was the PI for those. So as I mentioned, one of the things that I think exemplifies the work that we've done at Sandia in dynamic compression research is really integration of theory, computation, and experiment. And so, it's the kind of the nexus of these three, disciplines where we've really been able to make some success. Obviously we can't do a very large number of experiments, so simulation is very key so that we have some idea going into these experiments how they're going to perform. Obviously the experimental platform and diagnostics are key to being able to generate the states that we want to probe, and then also to probe those. And as I'll show, really taking the that experimental results and looking at through a lens of theoretical simulation has been very helpful in understanding what we're seeing. So on Z, we've tried to develop multiple platforms to really kind of expand the equation of state surface that can be probed. This is also being done at other facilities like NIF and Omega as well. But if you go back to, say, 15 years ago, we were fairly limited in the region of this equation of state surface that we could probe. We had the Hugoniot from single shock type experiments, and we could also do static compression and look at room temperature isotherms. So what we've been able to do over the last 10 to 15 years and on some of these advanced platforms is to really extend the Hugoniot by going to much higher pressures. We've been able to do shock and release experiments. There's some interesting work done as part of the fundamental science program at Z, looking at geological materials and really understanding vaporization. How hard do we have to hit those materials for them to cross the vapor dome, that type of thing. Of course, we've done ramp compression experiments where we've really limited the entropy that we're imparting into the sample, which enables us to get to very high pressures and densities, but keeping temperature low. And then we've kind of combined these platforms to be able to do shock ramp, where we initially shock the material to get up to some elevated entropy state, and then ramp compress from there to be able to probe higher temperatures and high density states. And by varying that initial shock state, we can kind of span these regions here, in the solid state or up into the liquid. And so this has been very instrumental in being able to access various regimes that are off the Hugoniot, and has provided a lot of information on various materials. So how do we do this on Z? I'm showing a cutaway of the Z machine here. So this is, for those of you who are not familiar, it's a large pulse power facility. It's about 110 feet in diameter. So what I'm showing here is kind of half of it. This is the experimental center, or where the load is put in. We have 36 Marks-Banks capacitors that are on the outer perimeter. These get charged up over about a 4-minute time frame. We can store roughly 22 megajoules of energy. And that energy then is delivered through these transmission lines to the center of the machines, where we're basically compressing this energy in time and space. And we can use these laser triggered gas switches to kind of stagger the current pulses on these 36 transmission lines. And there's some other games that we can play, but that allows us to basically tailor the current pulse and shape it so that we're driving a current pulse that will prescribe the loading that we want for the type of experiment that we're doing. Now, sitting here in this center section, this is about a 10-foot diameter by 20-foot tall vacuum section. Right in the center here is where we put the experimental load. And this is a kind of an isometric view of a typical coaxial load that we refer to. If I show you a cutaway here, so we have basically this lower portion here is a cathode. We have a cathode stock that comes up. This region here is the anode. We have anode panels surrounding this. This is why we call it a coaxial load. We've got a central cathode surrounded by anode. And we're basically delivering all of this current into these feed gaps here. And that compresses the compresses the cathode and basically explodes the anode outward. And so this is what I'm showing as a flyer plate type load, where we have a thin anode electrode here that gets accelerated across a gap. And then we have samples here that we can impact and do a more traditional kind of shock experiment. We also have a load geometry that we refer to as a stripline load. And in this case, you can think of it that we've removed 3 of the anode plates. So we still have this central cathode stock here that comes up, but now we only have 1 anode plate alongside of it. And there's a current contact at the top here. And so what we're doing here is we're forcing all of that current to go through essentially 1 feed gap. And in this case, we're blowing the anode and the cathode outward in 2 directions here. And one of the advantages of this type of load is that you can have sample pairs here that are experiencing essentially the same magnetic field as a function of time. That's not true in the coaxial case. In the coaxial case, each sample is experiencing magnetic field that is kind of laterally displaced from the other sample. And so this gives us our highest precision type measurement for doing ramp experiments. So this is the workhorse load that we use for doing ramp and shock ramp type experiments. The coaxial load is mainly used for doing kind of flyer plate type experiments. But in either case, whether it's a coax load or a stripline load, if you kind of zoom into this what we call the AK gap, or the anode cathode gap, we basically have a cathode material and an anode material, and we're putting large current of order 20 megaamps of current through this gap, and that creates a magnetic field between the electrodes that's in the megagauss range. And that J cross B force creates a stress wave that then propagates into the material. And it propagates faster than the magnetic diffusion front. So you can imagine that with this amount of current, we're very rapidly heating up the surface. That increases the resistivity, causes the current to want to migrate into more pristine, cooler material. And so you end up getting this magnetic diffusion front that propagates quite rapidly into the material. But fortunately, for good conductors like aluminum and copper, this stress wave is actually propagating faster than the magnetic diffusion front. And so we can, in the case of ramp experiments, we can look at how this ramp wave is evolving as you propagate through thicker and thicker samples. Or we can just use that stress wave front as an impulse to launch a flyer plate to high velocity. So that's kind of how we do those experiments. We're talking about a lot of energy. So I'm showing you here a picture of what an actual load looks like before you put it in the machine. And this is what it looks like when it comes out. We store 22 megajoules of energy in the accelerator, and we're delivering about 2 megajoules of that energy to the load, which is the equivalent of a couple sticks of dynamite. And so these are very destructive experiments. This is the typical arcs and sparks picture that kind of shows what happens during discharge of the machine. These are the laser triggered gas switches, and you can see all this breakdown happening at the surface of the water, which is in this case actually being used as an insulator. And I always like showing this picture because you can see like where this ladder is coming up out of the water. There's actually an arc here going about a foot across to the platform here. These are supposed to both be at the same potential. So I mean, there's just a huge amount of energy that's being delivered during these experiments, and they're quite impressive. As I said, we've made a lot of progress in understanding these experiments by kind of coupling the experimental results with theoretical simulations. And one of the main tools that has been developed for this over the years is doing density functional theory. So I thought I'd put a quick little primer in here for what density functional theory is and how we use it. And the key here is this formally equivalent problem of taking the Schrodinger view, where you've got all of your electrons sitting inside of some external potential, all interacting with one another. This is the classic quantum many-body problem, which is untractable. It's outside of a few very simple cases, it's you can't solve it. The problem scales like n to the 5. So trying to do this on even small systems is extremely difficult. But fortunately, it was discovered back in the 60s that you can equate this problem to a non-interacting particle sitting in some effective potential. And this makes it much easier in that you're no longer a many-body problem. It's a one-body problem, and it scales much better. It's like n to the 3rd, something like that. And so this is taking a very difficult problem and casting it into something that is much more tractable. So what do the Kohn-Sham's equations look like? So here we're showing the Schrodinger equation. So effectively, you've got your kinetic energy term here, and then you also have a potential energy term, which has the electron and ion Coulomb terms in there. But then you also have this little piece here, which is referred to as the exchange and correlation. And this is something that we don't know a priori what this is, but it turns out some simple approximations work surprisingly well. So you can do something like a simple local density approximation, or some other flavor of exchange and correlation, and plug that in. So here what we're showing is, here's your exchange correlation functional. So you can take that, put it into your effective potential. Now you've got something that you can then stick into the Schrodinger equation, and you can solve this. And you do this in an iterative manner to try to minimize the energy, and that gives you the solution of this Schrodinger equation. So how do we do this in molecular dynamics? So we've coupled this Kohn-Sham problem into a molecular dynamics type problem. So effectively what you're doing is at each time step of your simulation,
you've got some configuration of your atoms and electrons in your system, and you're solving the Kohn-Sham equations for that particular configuration. So this is assuming Born-Oppenheimer approximation. So this gives you then your electron wave functions, and from that you can actually calculate then forces on all the atoms, and then you can propagate those atoms just classically, just using F equals ma essentially. That gives you a new configuration. You go back and you solve the Kohn-Sham equations for that new configuration. You figure out the forces, you advance your atoms, and you basically just continually do this for many, many time steps until you get to some more or less static case where you can extract and what your average pressure and energy and things like that are in the system. So here's a simulation little movie. See if I can make that work. Apparently I can't. Let me see if I can change my, no. Sorry, it's not going to be able to show the little movie, but if I did, it would basically just show these kind of atoms moving around, and you could, it's interesting that you can see these little, these bars here are essentially, put in place if the atoms are within a certain distance of each other. And so you can kind of see these bars kind of show up and disappear. And this is, this simulation here is of hydrogen kind of in the region of dissociation. It gives a nice little picture of kind of how this works. But for those of you who are interested, typically the simulations that are done at Sandia with Mike Desjardins and also some of the work at the University of Rostock, they use VASP. It's the Vienna Ab Initio Simulation Program. As I said, there's you can use various different types of exchange correlation functionals. You can use LDA, GGA. There's also variants of GGA. There's some hybrid functionals that have been coming out in the last 5 to 10 years. And then we're also starting to look at some non-local type functionals. So these would be referred to as semi-local. But there's also been some exchange correlation functionals that are being developed that are termed kind of non-local, some that include van der Waals types effects. So there's various flavors of exchange correlation that can be used, but the machinery is the same, this VASP tool. Typically, we can look at up to 256 atoms. It really depends on the type of system that you're looking at, the number of valence electrons that you need to carry. So we typically have a certain number of valence electrons that will keep in the calculation, and the rest of the electrons are considered as part of these projector augmented wave potentials, core potentials. Simulations are typically done in the canonical ensemble, and as I said, you basically just kind of let these things run out over thousands of time steps until you get to somewhat of a steady state, and then you can use statistical analyses to pull out pressures and energies and things like that. So I thought I would kind of use hydrogen as an example of how we've coupled these experiments with the simulation techniques to really try to understand what's going on. The nice thing about hydrogen is that throughout the years we've done a lot of work looking at the dissociation or the molecular to atomic transition. So I was going to start off by talking about work that we've done looking on the Hugoniot, where we're probing this kind of insulator metal transition at relatively low density and high temperatures. And then I'll transition into some work. This was part of the fundamental science project with Rostock, where we were looking at this insulator metal transition now at high densities and low temperatures using a shock ramp platform to probe this transition down in the 1 to 2000 Kelvin temperature range just above the melt line. And then it turns out there were experiments done back in the 90s using kind of a ring up technique with a gas gun to probe this transition. And this is in kind of the intermediate density and intermediate temperature regime. So we're going to take what we've learned from these first couple of experiments that I'm going to talk about, and then transition to kind of re-looking at the these conductivity experiments that were done by Nellis and coworkers back in the 90s. So as I said, this is a fairly straightforward problem looking at what we refer to as first principles molecular dynamics simulations. And the idea here is we're interested in looking at how molecular hydrogen goes to just this simple atomic fluid. This is a slide I've got from Mike Desjardins. He likes to show this. This is Pierre Henry Hugoniot, who's sitting here thinking, well, maybe it's not that simple after all, right? So this is kind of a snapshot of where we were theoretically with this problem back in kind of the 2000 timeframe up to maybe 2005. And what you can see here in in circa 1998, we've got a plot here showing some very recent data at the time from the NOVA laser facility, along with several different kind of chemical picture models that were trying to describe dissociation of hydrogen. And one of the interesting and unexpected things was that these data were coming out at much higher compression than some of the original models were predicting. That spurned a lot of interest in looking at this from a kind of first principles point of view. So if you fast forward a few years, we start seeing some Path-integral Monte Carlo type calculations and some other quantum molecular dynamics types simulations, and they're kind of showing results that are all over the place. And this is a plot that was pulled from a paper in 2005. Where they kind of threw everything out onto a plot here that includes, some of the chemical picture models, that included some of the early tight binding, some Path-integral Monte Carlo, and other various flavors of density functional theory. And you can see that these predictions were kind of all over the place as far as what we would expect for peak compression along the Hugoniot through this dissociation region. And I don't want to just pick on the theorists, because if you look at where we stood from an experimental standpoint back around 2010 timeframe, we're not that much better. Here I'm showing some of the Z data that was taken, some data from Omega, the Omega laser. And I'll point out also this Omega laser data was reanalyzed using some better standards for both quartz and aluminum. So actually in the 2010 timeframe, what the picture was even a little worse off than this. And we also have some Russian experiments where they were using some accumulating shock experiments to look at this problem. And in general, we're seeing fairly decent overlap between the experimental methods, but unfortunately the uncertainties were just very large and almost to the point where they weren't really useful for first principles theory to try to distinguish between the various calculations that were being done at the time, because this was a difficult problem, right? We've got a fairly large density compression, which means that uncertainties in shock velocity and particle velocity are going to get magnified when we look into this plane. And so it was just a difficult problem to deal with to try to get these errors down. So what have we done over the last, say 5 years or so? Is we've spent a lot of time and energy looking at standards for doing these experiments at high pressure. And quartz has become kind of the go-to standard for the Z and laser platforms. I'm showing here some Hugoniot measurements that have been made. We now have somewhere on the order of 250 Hugoniot points on quartz, kind of from a megabar to 15 megabar or so. And these are all at kind of sub% type uncertainties for shock velocity and particle velocity. So we have a very tight constraint on the quartz Hugoniot. And then we also did several release experiments where We had other materials that are transparent that become reflective under shock compression, showing here TPX and a couple of different initial density aerogels. So we have good tight constraints on the Hugoniots of these materials. And what we were able to do then is launch a shock in quartz, let that shock release into one of these lower impedance materials, and basically measure in particle velocity pressure space where we are. And it turns out if you use a simple Gruneisen type model to calculate a release path, you can determine an effective gamma for that model that would pass from this measured Hugonio state to this measured release state. And doing that over a variety of different impedance materials, we can develop a plot that looks something like this. So I think in this case, the red points here are TPX experiments. The cyan and blue are the two different density aerogels. And you can see that these all fall kind of on the same trend line, which would indicate that this model is doing an accurate job of treating the release through this entire release path. And then we can fit this to some functional form for the effective gamma. And what that allows you to do then is, for a given measured shock velocity in your quartz sample, you know where you are in PUP space on the Hugonio, and you've got an effective gamma that you can use then to calculate this release path. And it's a completely analytical release model, which is also helpful in doing error propagation. So we can use this model in a Monte Carlo type error propagation and capture all of the systematic and random errors when we propagate these things forward. So with that in hand, we went and did a few experiments doing essentially the best job we could for deuterium, where we're launching an aluminum flower plate into a cryocell that's composed of a front and rear quartz window, and then a deuterium sample in the middle. And what this allows us to do, we can use VISAR to measure the flyer velocity up to impact, the shock velocity in the quartz, the shock velocity in the deuterium, and you can see that. So this is an actual measurement for one of the experiments. Here's the aluminum impactor, impacts the cell. We've got a shock running through the quartz. Now we've got a shock running through the deuterium. And as the shock reverberates back and forth, all the subsequent shocks will catch up to the leading shock in this quartz rear window, and you see that happening here. And so here we can do very kind of targeted impedance matching right at this quartz deuterium interface using the quartz release model that was developed. And that gives us these data points here. So we've got 4 points kind of in the region of peak compression, and then we went up to much higher pressures here at just under 1.5 megabar. And these uncertainties and density for each experiment is on the order of a couple of percent, which is a huge improvement. It's about a factor of 5 improvement over what we had with the aluminum. And so now we can start looking at how does this data compare to, kind of the state of the art, first principles theories. So you can see up here, once we get through the dissociation region, we were seeing very good agreement between like PBE, this van der Waals DF1 and the experiment. So I'm just going to kind of get rid of that and focus now down here in this region. So one of the things that we did is said, okay, well, let's take this higher pressure gas gun data point and these other, these new points that we obtained with the quartz standard, and let's fit that in USUP and see what this looks like. And what you can see here, that's this dash cyan curve. Here's GGE. Here's a couple of the, this is PBE. Here's a couple of different flavors of this van der Waals type exchange correlation functional. And what you see is that the experimental results for dissociation, which is basically this plateau that we're seeing, the experimental results seem to be bounded by these different functionals. So PBE appears to show a dissociation at too low of a pressure, whereas these van der Waals functionals appear to be showing dissociation occurring maybe a little bit too late. The other thing we can look at is the maximum in compression. And so it turns out the PBE is seeing a maximum in this compression that's about the same as what we're seeing in the experiment, but it's at lower pressures, which again is, I think, due to the fact that it's dissociating at too low of a pressure. Whereas these other van der Waals types of functionals are showing a little bit too low of peak compression. So one of the things that we did is looked at what's really going on as far as dissociation between these three different or these couple of different functionals. And we did that by looking at the pair distribution function. So the peak of this G of R, which we're using as kind of a proxy for the amount of bound, bound molecules in the system. And so you can see if you look at PBE, this peak drops off as you go up in pressure. And the same is true with the van der Waals. However, there's this kind of pressure offset, right? So if we just kind of take this curve here, which is more or less just a guide to the eye, and we slide it over by 4 GPa, you can see that not only is there a shift in the onset of the dissociation between these two functionals, but there also appears to be a difference in the width. So if I just shift it, these curves are dropping off at a different rate. If I shift it and dilate it, I can actually get a fairly decent agreement here. And this is a 30% dilation. So what this is indicating is that the pressure width over which dissociation is occurring appears to be about 30% larger for this van der Waals functional than it is for PBE. So not only is there a difference in the onset, but there appears to be a difference in the pressure width over which dissociation is occurring. And I think that has something to do with the this peak compression here, right? And so one of the takeaways from this is that it appears that the van der Waals type potentials seem to be better. They're a better match for the onset of dissociation. They're still a little bit higher pressure than what we're seeing experimentally, but PBE appears to be perhaps showing a better width of over which pressure width over which dissociation is taking place. And one of the things that we looked at to try to kind of test that hypothesis is we asked the question, well, could we artificially reduce the tendency for this van der Waals functional to have bound molecules? So we came up with the idea of looking at elevated electron temperature calculations. And so we did took a couple of these simulations that were done and said, okay, well, let's make the electron temperature 2/3 higher than the actual ion temperature. And when we do that, you can see this point here goes out to higher density compression. This point here goes up to higher density compression in much better agreement with the experiments. So what this I think is again suggesting is that these van der Waals potentials perhaps are holding on a little bit too tight, and that while the van der Waals is showing a much better agreement with the onset of dissociation, the pressure width is better reproduced by the PBE in this case. And those conclusions are kind of summarized here in this slide. So now I'm going to go ahead and say, okay, that was looking at relatively low density and high temperatures. What about looking at low temperatures and high densities? And this turns out to be a region of interest. So we're going to look at this region right here, just above the melt boundary, and try to ask the question, how do we go from a molecular fluid to an atomic fluid in this regime? And this turns out to be something that's of interest to planetary physics, because it appears that metallization of hydrogen, which is coincident with dissociation, it appears that that's kind of a catalyst for helium basically coming out of solution. So looking at the phase separation of hydrogen and helium, that seems to be catalyzed by metallization of hydrogen. So this is an important question to ask as to what's going on in these big gas giants like Saturn and Jupiter, which are these big masses of a mixture of hydrogen and helium. So this was part of a fundamental science project that was done in collaboration with the University of Rostock. So if you look at this region here, just above the melt boundary, again, these are the various flavors of density functional theory with the different van der Waals functionals. This is a hybrid functional, and this is PBE. And I'm showing multiple curves because it turns out, these are light enough elements and we're at low enough temperatures in this regime that nuclear quantum effects matter. So if you ignore quantum effects, these solid lines would be where these different functionals would be predicting a first order phase transition from a mostly molecular to a mostly atomic fluid. If you start to include nuclear quantum effects, for deuterium, you get the long dashed lines, and for hydrogen, you get the short dashed lines because hydrogen's lighter than deuterium, and so it's you have a larger effect. Now notice as you get up to a few thousand Kelvin, these things kind of come together, and the nuclear quantum effects kind of become less important at these higher temperatures. But the takeaway here is that all of these different functionals are predicting a first order phase transition that would end in a critical point near a few thousand Kelvin, something like that, but at very different pressure regimes, spanning anywhere from 1.5 megabar out to 3 to 3.5 megabar. And so we set out to try to measure this experimentally using a stripline type load. So this is an isometric view. We've got this big copper block is basically part of the cryocell. This is a gas fill nozzle, so we can bring the deuterium or hydrogen gas into the cell. This is hooked up to a cryostat that allows us to cool this down and then condense a liquid into this region. If I show a cutaway of this, so here is our cathode. Here's our anode. So the current's going to be flowing in this gap here. And here's our cryocell, which is basically composed of an aluminum front plate. Here's our region where our deuterium sits. And this is about a 100 micron or 150 micron gap here. And then we have a lithium fluoride window. And what we did is we put a reflective coating on that window. So we had some probes here. This is a little hypodermic needle that has a bunch of different optical fibers. So we've got 7 fibers that we are pointing over here that are probing basically the rear surface of the deuterium lithium fluoride interface. And then we had a similar set of probes that were looking through at the aluminum deuterium interface here. And the idea is that we'd pump current through this gap, and it would be shaped in such a way that we would initially launch this electrode here up to a velocity of a few kilometers per second, impact the cell. That would launch a shock that would then come and reverberate in between the aluminum and lithium fluoride and drive the deuterium up to some state. And then the subsequent current pulse would basically continue to press and would provide ramp compression. So this would give us a kind of a shock ramp loading that would allow us to get to high densities and high pressures, but at reasonably low or relatively low temperatures. So here's some representative data. This is showing the current pulse. So it's a very, very long current pulse, about a microsecond long. Again, this initial ramp gets us to, launches that electrode to more or less constant velocity, impacts the cell, drives a shock. And then here you can see this is the velocity that is being measured at the upper probe, which is looking through the deuterium at the aluminum deuterium interface. And that lower probe is looking at the deuterium window interface. And so this is kind of a classic shock reverberation that brings us to a point here. And then we have subsequent ramp compression. Now, what I'm also showing here in green on this other axis is basically what the intensity of this upper probe looked like. And you could see that throughout the reverberation and some of the subsequent ramp compression, we're seeing through the deuterium, it's effectively transparent, but then that signal basically drops to zero. And then later in time, it comes back again as we go through peak compression. And then as the pressure is relieved, we drop back down again. And effectively what's happening is that this region here, we're seeing the deuterium go from a transparent to an absorbing state. So we're basically absorbing the probe light that we're using as for velocimetry. And then later, as we get to higher pressure, we're seeing metallization. So here we're seeing reflection off the deuterium lithium fluoride interface because the deuterium has become reflective. And again, go through peak compression, and then as the pressure drops, we drop back again across that boundary and go back to an insulating and opaque sample, and that signal goes away. So we also, in addition to velocity, we also used a couple of fibers to basically look at just light that's coming from the sample. And this is showing the result from the lower probe that's looking at the aluminum coating on the lithium fluoride surface. And this is light that gets sent through a spectrometer that gives us wavelength dispersion, and then that goes into a street camera that gives us temporal dispersion. So we're seeing this is wavelength and time. So here what we're seeing is just a fairly featureless light source that it turns out we actually aren't entirely sure where this light is coming from, but we believe it's coming from, if I go back a couple slides here, we have a kind of a plastic thermal insulator here that is holding these fibers that is going to experience some current flow. And we believe that that's kind of lighting up almost like a light bulb. And so that's providing our probe light here actually, which is more or less, kind of a featureless in wavelength and time. We are seeing some of these lines here are wavelength fiducials that we use to calibrate our system. This is a notch filter that's being used for the Visar laser. But outside of those regions, these are relatively flat, featureless emission. So this is what it looks like coming off of the aluminum coating. If you look at the probe that's looking initially through the sample, you see something quite different. And what we're able to do with these is we can basically take these two results and we can get a signal that gives us effectively the relative reflectivity of the sample with respect to aluminum. So we're basically just kind of overlaying these things in wavelength and time and dividing one by the other, and that gives us a relative reflection, or in this case, a pure transmission as a function of wavelength and time. So if you look at this region here, and we look at a line out of that, that's shown over on the right-hand side. So initially, we're looking through the deuterium at the aluminum drive plate because the sample is transparent. And as I said, as the pressure increases, we get up to somewhere around 1.5 megabar. This signal basically drops down to a minimum here, and we are sure that this is basically due to absorption. So the band gap is closing with pressure. It gets to the point where it's around the 2.5 or 2 eV or so, which is roughly the probe light here, and it becomes strongly absorbing. Then later in time, we see the signal kick back up again. We go through peak compression, and then we as the pressure drops, that signal goes away. If you look at a line out kind of in this peak region as a function of wavelength, you can see that outside of these fiducials and whatnot, that we have a relatively featureless signal here that is showing a reflectivity that's around 2/3 of what you would be seeing for aluminum in these same pressure conditions, which is indicative of what you would expect for deuterium if it became a weak metal. So we can take a series of experiments where we change that initial impact velocity to basically provide different initial temperature states. And these are 4 experiments that were done at along what we expect, or the loading paths here. And these come from simulations that are done using an equation of state for deuterium. These squares are indicating where we are seeing the strong absorption start. So it's more or less transparent in this region, absorbing in this region, and then this is the region where we see the strong increase in reflectivity, which would indicate metallic transition. And so based off of our experiments, we're seeing something that is out here closer to 3 megabar, whereas the region where PBE would be suggesting this transition would be occurring is where we're seeing evidence of strong absorption at that point. Now, I should point out that since we did these experiments, there have been some experiments done at NIF, where the squares again represent where they're seeing strong absorption. In their case, they were seeing the onset of reflection showing up here at around 200 to 250 GPa. It's a little bit lower than where we are seeing it, but both of these results would be indicating that it's at a higher pressure than you would expect based off of PBE. So far, it's looking like both at the high temperature, low density, and the low temperature, high density regions, we're seeing better agreement with the dissociation onset with these kind of non-local functionals as opposed to PBE. So that prompted us to kind of go back and look at some of the earlier experiments that were done back in the 90s by Nellis and et al., where they were doing conductivity measurements. And so I have this plot here that is now kind of trying to put everything on one page. So we've got pressure and temperature. So again, these are the predictions for the first order transition. We've got the experiments from Z and NIF on here. What I'm not showing is the region where the Hugoniot would be, but that's up in this region. And so again, we've discussed these Hugoniot results up at high temperature, relatively low density. We've discussed these results at low temperatures, higher densities, and this region right here is kind of where the Nellis et al. Experiments are, which is kind of in the intermediate temperature and pressure regime. So that we thought it'd be interesting to go back and look at what does the PBE and the different van der Waals functionals, how do they compare to these experiments? So one of the first things we had to do is go and take a look at what are the states that are being reached in these experiments. And it turns out that the original work, there was an error in determining temperature. So this is a plot here that comes from that the Nellis et al. Work. Where they're indicating that we've got here 2 different equations of state that were being used to determine the temperature state in these experiments. And they referred to one of them as, this was the sesame or curly equation of state. And this was a Ross model equation of state. One of the differences is that they pointed out is the Ross model included dissociation. And so they were indicating that this large temperature difference was due to whether or not the model was including dissociation effects. Turns out that's not quite the case. The reason being is that these temperatures here were calculated using an equation of state model for like I said, it was the Curly equation of state, and they would actually do hydrocode simulations that included the full ring up. In the case of the Ross model, it was not a tabular EOS. And so what they did in that case is they calculated the first shock step and then a ramp compression from there. And so what I'm showing here is this is the 2 different methods that were used by Nellis with the same equation of state. And so you can see there's a huge difference in the peak state And the only difference in these two simulations is that one of them includes the all of the entropy due to the ring up, whereas the second method is only including the entropy from that first shock state. So if you kind of treat both of these equations of state on equal footing, you'll see, and that's kind of what I'm showing here. So here the colors coordinate. So the red is showing full hydrocode simulations that include the full ring up, whereas the blue is showing just a single shock followed by ramp compression. So it's missing out on all the subsequent entropy increase. And then I've got squares for the Ross model, circles for the original curly EOS that was used by Knudson, and then diamonds are the more recent curly model that does a better job of dissociation, at least along the Hugoniot. And what you see here is that if you take this same, if you use the same model with the two different techniques, that's accounting for most of the difference that that was being ascribed to dissociation. We also fixed a kind of an error that was made in this semiconducting model that was used to kind of describe the experiments. So they were looking at the conductivity and fitting it to, like I said, the semiconducting model, which is just simply some conductivity here times an exponential function that includes the gap and your actual temperature. In the original fit, all three of these were, they were using this as an independent fitting parameter and came up with something that resulted in the need for a negative band gap to describe the data. I think it's more appropriate to look at the three highest pressure experiments, use that to basically determine a better value for this sigma naught, and then fit the rest, and that gives you something that is physically reasonable, and that this band gap goes down to 0 and then flattens out. And so if you look then at using this Curly equation of state, the more recent one, to determine what the peak states are, then this is what you would get for the Curly equation of state, pressure, temperature, and density. And then we repeated that with PBE, DF1, and DF2. So again, what we're doing here is we're fixing the pressure state, which is the highly constrained by the experiment, because the peak state of this reverberation really depends on the anvils that were used in the experiment and the impact velocity. And then we choose to fix the temperature as well. And then we varied the density until we match this pressure that we would expect based off of the impedance matching. So when you do that for all of these functionals, you can see that the densities that you reach are all slightly different to get to these same temperatures and pressures. And then these are the conductivities that come out of those peak states. So here's what that looks like when you look at conductivity versus pressure. So one takeaway here is that if you were to look at PBE, PBE would say that every one of the experiments that were done by Knudson and company should have been metallic. The conductivity, the lowest conductivity here is a few thousand inverse ohm centimeters, which would be a good, a reasonable metal. Now, what's interesting is if you plot the conductivity that's calculated versus molar density, you can see that things look a little bit more uniform in that you've got PBE here. The reason that you're seeing such large conductivity is because the molar density is high compared to what you would infer from these others. So here's what we have for energy gap versus pressure, same story. When you look at molar density, things kind of collide. And so what this led us to speculate is that perhaps the problem with PBE is the pressure is too high for a given molar density. And we actually looked at saying, okay, well, what if we were to fix the temperature or density and pressure instead of the temperature and pressure?
And it turns out no matter how we tried to match this experimental pressure, in every case, whether we're matching pressure and temperature, pressure or density, density and temperature, they all are showing conductivities that are metallic. And so what this is saying is that, again, no matter how you try to match the experimental pressure, the conductivity is consistent with the metal. And so PBE is inconsistent with the experimental work. And this is interesting in that there's been some very detailed comparisons of these various functionals with quantum Monte Carlo, and they see pressure errors relative to this quantum Monte Carlo that's kind of in the same progression that we're seeing. So PBE seems to be lower than van der Waals 1 and 2 as far as these pressure errors are concerned. The dissociation we see on the Hugoniot, as well as just above the melt boundary, PBE is lower than DF1 and DF2. And so what this is all saying is that perhaps the problem with PBE is that the pressures are too high for a given density. So when you take all three of these together, we have a pretty good understanding of what's going on in this metallic to atomic transition for all these different cases of high density, high temp, or low density, high temperature, high density, low temperature, and intermediate case. And one of the big takeaways is that this PBE tends to always underpredict the dissociation, and this stems from pressure errors associated with PBE. So with that, I'll kind of wrap up and would take any questions you might have.
All right, thank you very much for the really great talk. We're right up against the time limit, but my understanding is that we don't just get cut off. And so I'll read the one question that's been asked. If anybody else has a question, please ask it using the Q&A button there at the bottom. But the one question that's been entered here is by Nick Hartley. I'll read it. Do your high temperature results imply that there's actually an electron ion temperature mismatch, or just that the potentials are closer to reality if you assume a higher T sub E? Are there ways to potentially measure the temperatures independently?
So that's a good question. So there are ways to measure the temperature, and that's something that we're working on for a publication that will probably be coming out this year, is temperatures of those from those experiments. The elevated electron temperature calculations that were simply done to try to probe what these van der Waals potentials might predict if they had less binding, if you will. So we're not implying that there's a difference in electron temperature and ion temperature. I don't think that's the case. And we're also not implying that this is a better way of trying to do these calculations, is to treat them as two different temperatures. It was simply to look at, can we kind of explain what we're seeing in the dissociation region with these van der Waals functionals? Can that be explained by possibly having too tight of a binding of your tendency to maintain a molecular state? So I think obviously the way to go here would be to look at perhaps tailoring different functionals to try to describe this in a more consistent manner. And I think the approach here was just to look at can we try to start to identify what are some of the shortcomings of some of these exchange correlation functionals. That information then can be utilized by those that go into developing perhaps new functionals. So we're not implying that there's a difference in temperature, but we're just looking at what can we learn from doing these types of simulations.
Okay, I'll read one more question, and then I'll probably need to cut it off to respect the time of our APS support guy. I don't know if he's got a hard cutoff or not, but there's another question by Nick Taylor. How might you measure conductivity directly in Z? It's not a very friendly electrical environment.
No, it is not. So yeah, yes, I mean, that's something that we have actually thought about. I think that would be a very a difficult measurement to make because if you look back at that picture where I showed of all the the arcs and sparks, I mean that just goes to show you how nasty of a EMP environment that is at Z. So the question there would be, could we shield the signals well enough to be able to make a conductivity type measurement at Z? It's something that we've thought about. It's something that I think we'd like to do, not just for hydrogen, but for looking at other systems as well. And so, over the next few years, I think we're going to, look at trying to do that. But we're going into it knowing that it's going to be a very difficult measurement to make.
All right, and then last question, the APS guy says that there's no rush, and so we can go a little over time. So there's one more question that I'll read. It says, do ultrasoft versus norm conserving PAWs affect the results?
So this would be more of a question for my colleague, Mike Desjardins, but certainly, different PAW, different pseudopotentials could influence the results. Now these, the compressions that we're getting to in these experiments are not, we're not really getting to the point where you would see these, perhaps these pseudopotentials kind of interacting, if you will. So it may be that at the densities that we're at, they're not going to be that significant of a difference, but certainly if you were to look at much higher compressions, I would expect to see differences between harder and softer pseudopotentials. But
all right, thank you very much. That's all the questions. Thank you to all of the attendees for attending and staying a few minutes over. Again, if anybody has any nominations, including self-nominations to do these talks, please send them to one of the organizers. And in the meantime, look out for announcements in your email about the upcoming talks. Thank you very much.